Hi everyone, I'm Sean Bartell from the University of Illinois, and I'm going to talk about guided linking, a new technique we've developed to optimize dynamically linked code. Let's start with a motivating example. Let's say you're a developer and you have a function foo that calls a function bar. Bar is a very simple function and we'd like to inline it into foo. Modern compilers make that very easy to do. Even if the functions are defined in different files, all you have to do is turn on link time optimization. But let's say one of the functions is defined in a plugin and one is defined in a shared library. All of a sudden, there's no way to optimize this code. There's no option you can turn on or tool you can use that will let you inline a function from one shared library into another. The purpose of guided linking is to fix that and let you optimize code across the boundaries between dynamically linked libraries and programs. Guided linking is essentially an extension of link time optimization to work on dynamically linked software. It works on existing software without requiring any changes to the code. It enables existing optimizations to work across dynamic linking boundaries, and it also enables new techniques. We demonstrate a new code deduplication technique that works across multiple programs and libraries. Guided linking can speed up the Python interpreter by 9%, or if we optimize together multiple versions of the boost library, our new deduplication technique reduces the total file size by 57%. But I'll get into the results later. Most of the previous work on optimizing across dynamic linking boundaries has focused on dead code elimination. These tools have special implementations of call graph analysis that cover multiple programs and libraries, which makes them effective at dead code elimination, but they don't support any other optimizations like inlining. Our earlier work on software multiplexing allowed multiple programs and libraries to be combined into a single statically linked program, which could have arbitrary optimizations applied to it. However, software multiplexing forces the entire set of programs and libraries to be processed at once, and it can't be used on software that relies on features of the dynamic linker, such as dynamically loaded plugins. Now I'll give an overview of the ideas behind guided linking. There are basically two problems that prevent existing compilers from optimizing dynamically linked code. The first problem is that the compiler only sees one program or shared library at a time. When we're working on a program, the code for any shared libraries it uses isn't available. The same applies to plugins, which are just shared libraries loaded by the program during execution. The solution here is for the developer to provide a set of programs and libraries as one unit to the guided linking tool. We call this set of software the optimized set. Just like with link time optimization, we compile each object into the compiler's intermediate representation before optimizing the objects together. The main task of the guided linking tool is to move all of the code out of the optimized set and into a new library called the merged library. The original programs and libraries are left in place as wrappers that link against the merged library, so whenever they're used, the same symbol definitions as before will still be available. After creating the merged library, we can apply the compiler's existing link time optimizations to it, as well as our deduplication technique. Even though the existing optimizations don't know anything about dynamic linking, this technique allows them to cross the boundaries between the original programs and libraries, just as if they had been statically linked. Unfortunately, the process I just described won't work correctly in most cases. That's because of the second problem with dynamically linked code, which is that the dynamic linker can behave in ways that we can't predict at compile time. Any definitions we have in the optimized set could be overridden at runtime by other definitions outside the set, and the exact behavior depends on lots of environment variables and configuration files that affect the dynamic linker. We can't safely make any assumptions about how the programs and libraries will interact. Now, it is possible to get the merged library to work correctly no matter how the dynamic linker behaves. We just have to add lots of calls back and forth between the merged library and the wrappers that will be dynamically resolved in the same way the calls in the original code would have been resolved. However, all of this indirection prevents us from doing any optimizations on the code aside from deduplication, which defeats the purpose of using the merged library. Our solution to this problem is for the developer to provide a list of constraints on the dynamic linking behavior of their code. For instance, they can use a constraint that says this definition of foo will never be overridden by a different definition in a different library. With that constraint, we can avoid adding indirection to the code, allowing us to optimize it effectively. For instance, we can safely inline foo into its caller. We still use indirection, but only on parts of the code that don't have sufficient constraints. So that's the overview of guided linking. Now I'll give some more detail about the process from the developer's point of view. The first thing the developer has to do is to choose an optimized set. The optimized set can be an arbitrary set of programs, shared libraries, and plugins. The developer just has to compile them in the form of compiler IR. It's okay if some libraries or programs are left out, as long as the constraints account for that. The downside of using a very large optimized set is that you have to optimize and distribute the whole set as a single unit. So if you change a single library in the set, you have to redo the whole optimization process and distribute a whole new merged library. If the developer wants to avoid changing the way their software is distributed, they can apply guided linking to a small set of software that's already distributed as a single unit, like a single software package. An example of a larger optimized set would be an entire Docker container. Docker containers are already distributed as a single unit, and usually no software is added or removed after the container is built. So in this case, it's practical to use an optimized set that contains every program and library in the whole container. If you want to be really ambitious, you could even imagine applying guided linking to your entire desktop computer. You would need to have compiler IR for every installed piece of software, and every time you install new software, you would add it to the optimized set and perform guided linking again. Now I'll get into the details of how the merged library is created and how the constraints affect that process. First, let's assume no constraints were provided. We start by moving all code out of the programs and libraries into the merged library. Here we've moved a function called foo. However, we can't be sure that this definition of foo is the correct one to provide. Maybe the dynamic linker will use a different definition from a different library. So we leave the body of the function in the merged library, but we put the definition of the symbol foo in the wrapper library. The definition is now just a stub function that calls the actual body in the merged library. Now the dynamic linker will decide whether this definition of foo is the correct one to use, just like in the original code. We also have to make sure every reference to a function in the merged library goes through the corresponding stub function. We don't necessarily know what the correct definition at runtime will be, so we have to leave it up to the dynamic linker to decide. We have to keep all stubs around even if nothing in the optimized set actually uses them, just in case they're used by an external program outside the optimized set. Finally, we have to add some extra indirection in case the merged library is used in a plugin. Full details are explained in our paper. We've now created a correctly working merged library. Unfortunately, all the indirection we added prevents us from doing any optimizations other than code deduplication. So let's see how the constraints allow us to improve the code. One of the constraints the developer can use is called the no override constraint. The developer applies this constraint to a given symbol if they can guarantee that no definitions of that symbol outside the optimized set will override the definitions we have inside the set. With that guarantee, we can safely avoid calling the stub function for that symbol, and instead use direct calls to the body function, which enables optimizations like inlining. Aside from no override, there are 3 other constraints the developer can use, each of which enables an independent improvement to the merged library. The no use constraint can help us make the stubs private, which in turn lets the compiler delete them if nothing uses them. The no plugin constraint allows us to avoid adding plugin-related indirection. And the no weak constraint allows us to keep stub functions in the merged library. Full details of each constraint are explained in the paper. If all 4 constraints are available, we can almost optimize the code as if it had been statically linked, modulo some special features of the static linker like comdats. A different combination of constraints can be applied to each symbol used by the code. In practice, the developer will choose some constraints to apply globally to the entire optimized set, and then add exceptions for a few symbols. This example shows the full constraints we used for Python, which is the only program we evaluated that required any exceptions. We apply all 4 constraints globally, and add exceptions to the no use and no plugin constraints for plugin code. There are also some exceptions needed for the standard libraries, but those are built into the guided linking tool, so we don't need to specify them here. Now I'll go over our results. We implemented a guided linking tool based on the LLVM compiler. The first program we benchmarked with guided linking is the Python interpreter. For the optimized set, we used the main Python program, 101 plugin modules, most of which are included with Python, and a few more libraries and programs used as dependencies. We applied all 4 constraints to the code, which implies that we can't use any new plugin modules or programs outside the optimized set. That wouldn't make sense for a typical Python package, but it would be perfectly practical in something like a Docker container where we know exactly which modules will be used. For our baseline, we applied link time optimization and profile guided optimization separately to each program, library, and plugin. The guided linking version used LTO and PGO on the merged library. We evaluated Python using the PyPerformance benchmark suite. Here are the speedups we get on each of the benchmarks. On average, we get a 9.2% speedup over the baseline. In the best case, we get a 32% speedup, and in the worst case, we get a 6% slowdown. There are only 4 out of 61 benchmarks that slow down. We believe these slowdowns are caused by issues with code layout in the merged library. In the benchmark where we get the 32% speedup, most of the CPU time is spent in a plugin module called Pickle. This module is processing Python dictionaries, so it has to call the pydictNext function over and over again, which is defined in the main Python library. Guided linking gives us a huge speedup because we can inline this function from the library into the plugin. Now let's look at a different kind of experiment. It's very common to have multiple versions of the Boost library installed at once because you're using different programs that require different versions of the library. The same thing can happen with protobuf. That leads to a lot of unnecessary code duplication. In this experiment, we optimized together multiple versions of the same library in order to reduce the size. After using guided linking to make a merged library, we reduced its size with our function deduplicator, which merges identical functions into one without affecting functionality. We only used one constraint because the others have the potential to cause compatibility issues with programs that use the libraries in certain ways. When we applied guided linking to 11 different versions of the Boost libraries, we got a 57% reduction in the total size of the ELF files. On 8 versions of protobuf, we got a 31% size reduction. For our final experiment, we applied guided linking to Clang and LLVM. We configured LLVM to build more than 100 shared libraries. This isn't the most efficient configuration for LLVM, but it demonstrates how guided linking performs on a very large number of libraries. For constraints, we tested 4 different configurations. That ranges from closed, which assumes that no external code will use the LLVM libraries, to interposable, which imposes no real restrictions. We used LTO and PGO for both our baseline and the guided linking version. In order to benchmark Clang, we used it to compile and link SQLite with the O3 option. Here are our results, showing SQLite compilation time and total binary file size. The baseline is on the left of each graph. For the closed configuration, which uses the most constraints, our optimized version of Clang is 5% faster and 13% smaller than the baseline. For the open spurious configuration, which is compatible with most external programs that use the LLVM libraries, our optimized version of Clang is still 5% faster and 5% smaller than the baseline. On the other hand, both of our 2 least constrained configurations are larger and slower than the baseline, because with so few constraints, we need to be very conservative and add extra layers of indirection. Now I'll talk about some ideas for future research to build on guided linking. The security effects of guided linking need to be researched. There may also be new security techniques enabled by guided linking. We can try to improve the merging process by selectively leaving some body functions in the wrapper libraries, which may reduce the amount of interaction. The current implementation of guided linking goes to great lengths to maintain compatibility with existing dynamic linkers. Future work could try modifying or replacing the dynamic linker to make guided linking work better. We could take some of the highly sophisticated function deduplication and merging ideas from the literature and implement them in the guided linker so they could be applied across multiple programs and libraries. Finally, guided linking may create new opportunities to optimize inter-process communication by putting the code for all processes into a single library. In conclusion, we've shown that guided linking can be used to optimize dynamically linked code by working on an optimized set of software and using developer-provided constraints on the dynamic linker. We've used guided linking to speed up software by 5 to 9% and shrink it by 13 to 57%. That's the end of my talk. If you're interested in guided linking, you can find the source code on GitHub or send me an email.